just establish that it's differentiable on the open interval. All right. So the hypotheses are met. We're going to apply the conclusion now. All right, so we're going to find all values guaranteed by the mean value theorem on the interval (1 to 3). All right, now, a mistake that people make, they're like, oh, I have to remember that formula, the mean value theorem formula. No. Calculus is not something that's formula driven. We're going to do a lot of geometry related stuff, actually starting later today. That's formula driven. Like you say, I have to remember the formula for the volume of this or the surface area of that. That's a formula. Calculus itself is based on relationships and processes. So you have to remember the example that I gave you on Wednesday about with the easy pass, finding where the instantaneous speed is equal to the average speed. Okay, the mean value theorem says that if those hypotheses are met, then there is at least one place where the instantaneous rate of change is equal to the average rate of change. And if you remember that relationship, then you could say, oh, instantaneous rate of change equals average rate of change. So you set the derivative equal to the difference quotient. And then it's going to be an algebra problem. All right, we already found the derivative when we were checking the differentiability. So we're just going to copy that into this relationship, not formula. This is a relationship. What do we have to set it equal to? What do we have to set it equal to? Square root of 2 divided by 2. All right, guys, if you haven't a complete refusal to look at your notes, we're going to stop taking notes, okay? Because there's no use to them if you're not going to look at them and reference them. We already did this, square root of 2 divided by 2. All right, so now this is an algebra equation, okay? Now, before we get into solving this, okay, cross multiplication is a gimmick. There's nothing in math that says you can do this, okay? What you're actually doing when you think you're cross multiplying is you're multiplying both sides by the denominator on the left and both sides by the denominator of the right side. And it looks like you're doing this. There's nothing in math that allows you to do that. So I certainly don't want to see this, okay? People doing this, I don't want to see that. I want to see that about as much as I want to see repeating decimals and lattice method. Okay? Make sure you put your name on that lattice method stuff next time, Parker. Math League, lattice methods. You had to use calculator on the Math League. You have to use lattice. All right, we're just going to do the algebra to solve this for x. Now, if we look at our graph, okay, we're just going to go back and look at our graph. We're looking for tangent lines that are parallel to the secant line. So looking at that graph, how many tangent lines can we draw that are parallel to the secant line? One. Mean value theorem says at least one. All right, so one fits the bill of at least one. So we could draw in that tangent line right now. All right, and you can see that there's one value there. All right, as long as your sketch is representative, then your sketch should show how many tangent lines you should get. Okay, so if you didn't graph square root of x minus 1 right, and you have it changing concavity and stuff like that, then you're going to see more than one tangent line. Doesn't make it correct, because if you have an incorrect graph, you can't draw any visual conclusions based on that. I'm going to divide both sides by 2. And then I'm going to divide both sides by the square root of 2. You could have done that in one step if you wanted. 2 steps is fine. Also. Now, do not rationalize that right side, because what are we going to do algebraically as our next step? We're going to square both sides. So if you had rationalized it and then squared it, you have to reduce it. Just leave it like this and square it. It's reduced. Right, now, before we go on, we have to talk about some things that we covered last year. This was called a radical equation. And you have to understand that when you change the form of an equation, and squaring both sides falls into that category, you can introduce extraneous solutions. So we have to check to make sure this is actually a solution to the equation. So we're going to take this 3/2, substitute it here. 3/2 minus 1 is 1/2. Square root of 1/2 is 1 divided by the square root of 2. Multiply it by 2, we get 2 divided by the square root of 2. And 1 divided by that is the square root of 2 divided by 2. Okay? You can't say, well, that's the only solution. It's got to be it. There's no theorem that says that. There's nothing in math that says that. It's the only one, so it's got to be it. You have to check, because it could be that there's no solutions here. Okay? You say, oh, but you said there has to be at least one. Yeah, but this is how we can check to see if our work is correct, though. All right, so if we go back to the graph here, and we look at this point of tangency, just go down the x-axis. What is that x value right there? 3/2. Right, the mean value theorem allows us to find that x value. Or, depending on the situation, it could be more than 1. Okay, now follow-up question. Without substituting, what is f prime of 3/2? Is that louder? Square root of 2 divided by 2. All right, let's think about what we just did. We started off by finding the average rate of change, which is the slope of the secant line. Then we found the x value where the tangent line is parallel to that secant line. So therefore, the tangent line and the secant line, they're parallel, so they have to have the same slope. Okay? That's why we didn't need to substitute to find that. Okay? And a mean value theorem, again, allows us to find that value.
Let's take a gander at this for 1 second.
Sure.
Sorry, guys.
All right, back to the task at hand. We're going to go back and hit something you talked about a couple of years ago and look at the calculus involved. All right, what's this equation for? Parabola. All right, it's a standard form equation for a parabola. Okay, it could look like this. And that's if A is greater than 0. Could look like this. And that's if A is less than 0. All right, x coordinate of the vertex. Anybody remember how to find that? What x is equal to, the x coordinate of the vertex? Something you covered in Algebra 2. Negative b divided by 2a is correct. We're going to look at where that comes from today, because you were probably just given that, so this is what it is. All right, so what I'm going to do in each of these parabolas is I'm going to mark where the vertex is. All right, now, remember in calculus, differential calculus, we're talking about instantaneous rates of change, which are slopes of tangent lines. So if you look here at the vertex of either one, what kind of tangent line do we have? Horizontal. So what's the value of the derivative at the vertex? 0 here. How about here? Also 0. Okay, so we're going to take this. We're going to find what f prime of x is equal to. Now, what are a, b, and c? Constants. Okay, it could be positive, could be negative, could be 0. All right, so we're going to differentiate this term by term. What's the derivative of ax squared with respect to x? John? 2ax. Derivative of bx with respect to x? Plus b. Derivative of c with respect to x? 0. What do you think we want to do with this 2ax plus b? Because we're talking about what's going on at the vertex. Set it equal to 0. Okay, and then do what with this equation? Solve it for x. All right, so subtract b from each side, and then divide by 2a. That's where that negative b divided by 2a comes from. Okay, comes from calculus. That's why you were just given it, said this is what it is. So we just filled in a blank there. And we'll be doing that with a bunch of things this year, because a lot of the things that you use in lower level math, the derivations come from calculus. One over to Brody, please. All right, that's about it for the mean value theorem. We're going to move on now. What we're going to talk about as our next topic, actually, in case you haven't figured out right now, I give it to people straight here. The topics that people tend to struggle the most on in the AB curriculum, they're all in, or the two topics are in this unit, and they're the next two topics that we're going to cover. All right, and the difficulties that people have with them are not because of the calculus that's involved, it's because of the algebra. So we have to set up algebraic equations, and that's something that you don't have enough experience with. Okay, so we have to make sure we work on that. All right, this section is called optimization. You'll also hear them referred to as applied min-max problems. So we're going to look at some application problems involving optimization, finding maxima or minima. We're going to start with a very simple example. It says a metal box without top is to be constructed from a square sheet of metal that is 10 inches